work into wireless and IoT security. In this chapter, we will look at some more security models in mobile devices. We will look at the security models of all the major smartphones. We look at bring your own device and security and enterprise mobility management. Okay. In the Android security model, we look at the security model, these Android sandbox, file system permissions, the S3K security features, routing and unlocking devices, and the Android permission model. The Android is built on Linux kernel. Android applications use process sandboxing for security, which means they run on its own virtual machine. Each VM is isolated within its own Linux process. Android does not rely on Java VM to enforce security. It looks to the Linux kernel. Okay. So Linux kernel is a foundation for Android security, and it provides key security features. User-based permission model, process sandboxing, extensive mechanism for inter-process control, and ability to remove unsecure elements from the kernel. So this is the Android sandbox and file system permissions. Android sandbox adapts the Linux multi-user based protection to identify and isolate Android applications. Applications running sandboxes have only limited access to system resources. Memory cards in one application does not create security issue that compromises the overall security of the device. Linux file system permission ensures one user cannot access files of other users. In Android, prevents one application from accessing other applications. Each application runs as a user with its own set of permissions. Developer must explicitly grant permission to expose files to other applications. Some of the SDK security features are police prevent stack overflows, tools protect against leaking kernel addresses and integer overflows during memory allocation, techniques for formatting string protection, hardware-based no-execute parameter or control to prevent code execution in the stack or heap, can encrypt data through cryptographic application programming interfaces which support primitive primitives. In Android security model, only OS kernel and small subset of core application run with a root permissions. Rooting a device gives someone privileged root permissions. Can override Android OS security. It increases the risk of malware infection. Some versions of Android allow users to change boot sequence to bootloader, then can upload alternative version of OS or application with root permissions. In the modern day Android phones, rooting is extremely hard. Every single manufacturer adds their own security, and if the OS detects you rooted it, sometimes it will shut down. This is the Android permission model. Applications run in sandboxes. They are only a limited access to some resources. Restrictions implemented by a deliberate lack of API. Others are protected API status. Only trusted applications can access protected APIs. They are protected by permissions. To use APIs, application must receive permission from device owner. Another security concern with a rooted Android device is that Android natively supports active content such as Flash, Java, JavaScript, and HTML5. This can open attacks for malware. Additionally, features such as always on, listening, An auto content update can be vulnerable to misuse, and they can dynamically enable or disable features, provide location information, or record conversations. Let's look at Apple's iOS security. Similar to Android, we look at the security model, application provenance, iOS sandbox, the security concerns, permission-based access, encryption, and jailbreaking in iOS. The Apple security model uses a walled garden approach to security. It will restrict access to and downloads from websites other than app stores. App developers must register and pay to become official iOS developers. I believe it's like $99. They're given a digital certificate which assigns the applications. Only digitally signed applications from authorized developers can be uploaded to App Store. This certificate ensures integrity of application. Code cannot be tampered with after release. Application provenance through Apple iOS Developer Program and iOS Developer Enterprise Program. It ensures the users can trust an authenticity and integrity of application in App Store. It does not guarantee safety of apps, increases odds that application developers will be held accountable for their work, deters developers from publishing malicious code. Apple isolates applications by running each in its own sandbox. Apps cannot determine whether the other applications are present on device. Isolation achieved by preventing an application from gaining access to OS kernel or obtaining root privileges through driver installation. The result is a strong protection from malware. Isolated apps still theoretically vulnerable to web or network-based attacks, like attack on Safari browser via malicious web page. Could gain control over browser's logic. Malicious payload, although segregated, is free to obtain system-wide access to calendar, address book, and cameras. Can steal any data that passes through browser application, including web passwords and login credentials. Apple iOS apps require an honest permission only when doing the following: accessing location data from the GPS, receiving remote notification alerts from the internet, initiating outgoing call, sending an SMS or email message. Apple changed some permission structures to address lack of granularity in user permission. The new choices are allow once, don't allow, or only while using the app. Apple provides a full device encryption, requires a key resides on device. iOS uses layered approach. Certain data like email files, messages, and other personal data doubly encrypted. Jailbreaking gives honest root or super user privileges, enables them to offer an application provenance model. Owners can download application from wherever they like. It comes at a cost of security. Let's look at the platform security, application security, and security features of Windows Phone. The platform application security protect applications through isolation, uses strict application provenance. Windows Store follows the same model of the Apple App Store. Only strictly vetted applications are released on downloaded devices running Windows Phone 8. Okay. Security boot process supported by TPM, encryption of data and applications, maintaining device and firmware integrity, sandbox model to ensure application isolation from the system, resources, and other application runtime. Windows 8.1 was made obsolete in 2016 with the introduction of Microsoft Windows 10 Mobile. Let's look at the Android version evolution. In 2008, version 1.0 was introduced. It was a very basic OS with integrated Google Apps. In April 2009, version 1.5 Cupcake introduced a framework for third-party apps. In September 2009, version 1.6 Donut had supported CDMA and different screen sizes. October 2009, version 2.0 2.1 Eclair had navigation and speech-to-text functions, amongst others. May 2010, version 2.2 of Froyo had flash support and several under-the-hood performance upgrades. December 2010, version 2.3, Gingerbread had more aesthetic changes to the screen layout and color scheme. February 2011, version 3.0 to 3.3, Honeycomb was a tablet-specific release of the Android with different UI. October 2011, version 4.0, Ice Cream Sandwich, for many of the UI experiences on Gingerbread to the smartphone. 2012 to 2013, version 4.1 to 4.3, Jelly Bean introduced Google Now and Quick Settings panel. October 2014, version 4.4 of KitKat introduced OK Google and reimagined the screen layout and UI. November 2014, version 5.0 Lollipop introduced a material design concept which provide material themes for third-party app developers to use in their mobile apps. 2015, version 6.0 for Marshmallow introduced granular third-party apps permissions. 2016, version 7.0 NuGet introduced Google Assistant and third-party application notification by batch. 2017, version 8.0, 8.1, Oreo introduced an enhanced notification channel for third-party apps and ways to make it easier for vendors to roll out software updates. 2019, version 9.0 of Pi prevented application from running in the background, accessing camera, microphone, and sensors, and provide a clear notification to users if any device isn't being accessed by the application. 2019, there was a version 10 actually changed their naming convention. It was no more dessert nicknames. Update the permission systems that gives the user more control over how apps access location data, as well as an expanded system for protecting unique device identifiers. 2020, version 11.0 introduces expanded and more granular permission that are accessed to devices on a single use basis. Let's look at the iOS evolution. In 2008, version 1.0 was introduced, and it launched with the In 2008, version 1.0 was launched with the introduction of iPhone, described as an OS version of Apple's version X desktop OS for mobile devices. 2008, version 2 introduced App Store, push email, and GPS. 2010, version 3 introduced the iPhone 3GS with 3G carrier support. 2011, version 4 introduced CDMA support. 2011 also version 5 introduced Siri and iCloud with Twitter integration. 2012 version 6 introduced LTE support and Facebook integration. 2013 version 7 introduced AirDrop for iOS and Notification Control Center. In 2014, version 8 introduced Apple Pay, iCloud Drive, and Handoff. 2015, version 9 introduced Android migration. 2016, version 10 introduces access to Apple apps for third-party developers. 2017, version 11 introduced Apple Pay Cash, updated Siri, Wallet, and Maps, as well as a new App Store. 2018, version 12 improves Safari privacy protection, which prevents browser activity tracking. 2019, version 13 features quick unlock with facial recognition and improves Siri voice. Yeah. These are the security challenges of handoff type features. Apple released handoff in 2014, allow users to move seamlessly between devices, continuing where they left off. Meaning, if you have a Apple iOS mobile device or a tablet or a Mac, you can put your phone down and go to the Mac and continue where you left off. Each device must be connected to the same Wi-Fi network and be sent to the iCloud with the same Apple ID. Requires inter-device continuity using both Bluetooth 4, Wi-Fi direct connections. Provides communication, data, and workflow between devices. Could lead to data being handed off to unmanaged devices or even to unauthorized apps. Okay. Emergence of bring your own device brought by shifting corporate strategy. Employees prefer to use personal devices for some work tasks. BYOD exacerbates the risk of data leakage because thousands of uncontrolled mobile devices have access to whole company data. Apple iPhone is the ideal bring your own device client. One iOS, which is also a closed system. One or two models of each version of the device. Android OS phones are bring your own device nightmare. OS is severely fragmented. Also, around hundreds of various devices from multitude of manufacturers. To successfully manage bring your own device, you need to have either mobile device management or mobile application management or enterprise mobility management. So let's look at what is enterprise mobility management or EMM. This is a framework that consists of sets of people, processes, and technologies required to manage mobile IT within the enterprise. It's a turnkey solution that helps IT departments secure and manage broad range of OS and devices. Has a wide scope that includes disciplines such as security, application management, and financial management. Let's look at some of the common MDM tasks. Your inventory management, where you maintain device inventory maintenance, physical tracking of mobile devices, data provisioning, device management, device registration, device activation, device configuration. Those are software distribution, patch updates, mobile optimization, software packages. You also have security device management, in which you use authentication, which you may use Active Directory or other single sign solutions, password enforcement, remote device wipe, either a whitelist or blacklist. You have data protection, which is encryption, backup or restore, data tracking, and remote support. There are server portals, diagnostic, remote control, and origin compliance. MDM is typically built on a client-server model. MDM server controls and manages client agent installed on the mobile device. Can automatically detect a device on the network and send and collect information, send updates, and configure device remotely. Allows for remote locking and remote wiping of company data from a lost and current device. Updates can be sent to one or group of devices, all iOS 8 or all version 4.4 Android or Windows 8.1 simultaneously. Mobile application management and is assistant delivering software, provides a distribution platform for apps like the application lifetime management, and handles the software licensing configuration and usage tracking. In this chapter, we looked at security models for and features for Android, iOS, and Windows. We looked at bring your own device and security and the different types of enterprise mobility management options.